Okay, so we're recording the discussion of homework number 12. We pulled images, and if you have any questions, please feel free to chime in on the in the chat or just speak into your microphone. So homework images, homework number 12. Here we go. So the first question I asked was numbers 20 and 21, and then 25, 27. For 20 and 21, all you're really being asked to do is find the numerical value of the given function at the indicated point. Use h equals 0.001. Really, you could just use your calculator. I mean, I think that would be okay if you just use your calculator for that, for numbers 20, 21, and 25. I mean, yes, if you were to do it by hand, you would do this. For number 20, you'd be doing f of 0 plus 0.001 minus f of 0 over 0.001. And you wouldn't do a limit at all. You would just have to just solve that. That's what you would do. But if I were to just punch this into the calculator, x cubed minus 4x at 0, remember we did this before. I just go to my TI calculator right here. TI Smart View. It's just taking a little while. Should have opened this earlier. It's my fault. Okay, no. So yeah, so you go alpha, window, option 3, and it's x cubed minus 4x. Okay, let me, it's kind of hiding. So with respect to x cubed minus 4x at x equals 0. And that's what I get. Now, remember, the calculator is doing a little differently. They're doing something called symmetric difference quotient. The calculator is doing this. It's doing f of 0.001 minus f of negative 0.001 over 0.002. So it's doing a plus h and a minus h. That's what the calculator is doing. And then this right here is 2h. And remember, symmetric difference quotient means this. So like you have a right here. This is a plus h, a minus h. And so you just take the slope between these two dots that are making them really big right now. If you did it just using these two, that's fine also. It's just getting used to how to find numerical derivative. So if you use the calculator, that's totally fine. So that's that one. You do the same things for 21 and 25. And 25 is kind of interesting because what's happening to that's going to be a cusp at x to the 2/5 power. And so it says the derivative is 0, which is interesting. So let's actually look at 2/5 really quickly. Let me repeat this. And let me go ahead and clear my writings. So let me change it to x to 2/5. 2/5. Delete, delete, delete. So it says 0. Now, why is it saying 0? It's saying 0 because the graph looks like this. That's how the graph looks. The calculator is doing, remember, f of 0.001 minus f of negative 0.001 all over 0.002. That's why it gives 0. But really, I know the answer is supposed to be D and E. Because the left-hand derivative is going to be negative infinity, and the right-hand derivative is going to be positive infinity. Remember, this is going to be a cusp. And we'll once we know the shortcut rules, we'll explore this again on Tuesday next week, and you'll get a better understanding why that really should be D and E for that one. So so it is a little deceiving. So that was kind of part of the homework too, because we did talk about times when it can be deceiving. Like absolute of x over x was another one we saw that was a little deceiving. So that's that one. Also for homework, I asked you guys just use the n derivative functionality in the calculator to graph these here, so 27 and 29, and see if you can actually identify what the derivative will look like, right? So I did this for 27, 29. So if I did negative cos x, so very nice if you have this already stored. You don't have to retype the derivative over and over again. But I did negative cos x, negative cos x. We'll graph in the standard window. Actually, we'll graph in trig. So there's negative cos x, and there's the derivative. The derivative I'm actually going to trace in red. Anyone want to tell me what this looks like? This is the derivative. This is the original. Remember, the original is negative cos x. Anyone want to take a stab with the derivative, what the equation would be for the derivative?
Is it just sine x?
It's a sine x, exactly. Mm-hmm. So what this means is that the derivative of negative cosine x is sine x. So we're going to talk about trig derivatives probably in our third unit when we November sometime. We'll definitely have that discussion. Yeah, but yeah, that's what it is. It is sine x. And when we start taking slopes of tangent lines for the original, like here's the slope of this tangent line at 0. Sine is 0, 0. Or here, this happens at pi. What's sine of pi? 0. So it's interesting when you see this stuff. Starts, a lot of things start making sense. Hopefully they do. So that was that part of the homework. And then we had 39 as well as 40 through 45 all. So let's talk about that. Should have said 39 through 45 all. I know why I put 30, but 39 is kind of a standalone problem. So for 39, here is what's happening there. Hold on, just so many windows up. Okay, there we go. Rotate it. So this is a great problem. This is a problem that's done often on the AP exam, and actually worksheet 9 and worksheet 10 go over this kind of stuff, which we're going to practice in just a few minutes. So where a and b are constants, this is a piecewise function. Okay, fine. So we want to know where it is continuous. So all you need to do for continuity, you really just need this to happen. And what is the left-hand limit? Limit as x approaches 1, because 1's a boundary here, right? Of f of x. 1 from the left side, mind you, and limit as x approaches 1 from the right side of f of x. Well, that's easy. That's just 3 minus 1 equals a times 1 squared plus b times 1. Remember, you're plugging 1 in. So 2 equals a plus b. That's how you get that. Of course, I don't know what a and b are because I have one equation. So I need another relationship between a and b. Now we got to make it continuous and differentiable. So if you want to make it differentiable, the left-hand derivative has to equal the right-hand derivative. And going back to continuity one more time for part A, you need f of 1 to exist, but we do know it exists because 1's included here. That's why I really focus on that second condition. The left-hand limit has to equal the right-hand limit. And of course, once you get that, that's going to equal f of 1. That'll take care of it. The third condition will take care of itself. We'll be okay. Because I'm forcing it to be continuous. Left-hand derivative equals right-hand derivative for differentiability. So the derivative of the left hand is going to be just, so you could kind of write like this now. I like to use this little accent mark to show I'm taking the derivative. And the right side of 1, I'm doing that. So this is the left-hand derivative, meaning the limit as h approaches 0 from the left, of f of 1 plus h minus f of 1 over h, because I'm evaluating this at x equals 1 eventually. Or you can write it as the limit as x approaches 1 from the left side of your derivative. Well, the derivative here is 3 minus, 3 minus x is the function to the left of 1. The derivative of that's going to be negative 1. Where a derivative of this is going to be 2. That one's a little tricky, actually, because I haven't really taught you guys the shortcut rules yet. So if you got a little stuck on this one, I don't blame you. The derivative of ax squared, well, first of all, whenever you see x squared, we know the derivative is 2x. We've talked about this. Whenever you see x, the derivative of x we know is 1. I'm going to just focus on the x bit. Then you have your coefficients. So in this case, you're going to say a times 2x plus b times 1. Then you can plug in 1 for x. So you get 2a plus b. So now you got two equations here. You can solve for a and b. And I trust you guys can do that. I don't need to do systems of equations. You guys should know how to do that by now. That's 4 or 5 years ago. But that's what you would have to do, is you have to take the derivative of each of these expressions. We did talk about for constants, that's just going to be, for linear terms, just going to be the slope you see. And then for x squared, it's just going to be 2x. And then you just attach the coefficient next to them. Oh, derivative of x squared, so if y equals x squared, the derivative is 2x. That's from the section 3.1 notes. One thing that'll help is that when you guys watch the video over the weekend, you'll see the shortcut rules. It'll be really easy. You'll know. Cool, you're welcome. Okay, let me go and clear that. And then the rest of these here were more conceptual, which actually is kind of good to do because we need to talk about this conceptual stuff for we get too ahead of ourselves. So let me expand that just a bit. So for 40, if you have a derivative, is it continuous? Of course it is. Differentiability leads to continuity. If you're continuous, you have a derivative, maybe, not necessarily. So that's going to be a false for 41. Remember, continuity doesn't necessarily mean that you have differentiability. For example, you can have a corner. You can have something kind of weird like that. It's continuous there, but not differentiable. Which of the following is true about this graph here, x to the 4/5 at x equals 0? You could graph that. If you graph that correctly, you should get a cusp. You're graphing the calculator, and it's going to be a cusp because it looks like this. So go based off looks for now. We'll revisit this next week, or once we learn the shortcut rules, you'll understand why. But remember, the whole point of a cusp is that the left-hand derivative is going to be infinite in nature as well as the right-hand derivative. However, they're going to be opposite in sign. In this case, you get that. And you can see as you get closer to 0 on either side, it's going towards negative or positive infinity. For 43, what you probably would want to do is just use your calculator. In fact, I could probably go to my calculator here. Let's change that to the cube roots. So you could do math and then option 4, x minus 1. And I'll leave I'll just quit out. And you hit alpha window, option 3, x, oh, come on, x, alpha trace y1, x equals, let's try 1, see what happens. So it says 100, which is kind of weird. You could try different numbers, like for example, if I do like -1 or 2, I get those that seem a little bit more reasonable. So why is 100 unreasonable? Well, let's actually look at the graph as well. Like 0.333. So let's go to over here. Let me turn this off. Actually, I'll leave both of them on. What the heck? We'll graph in the standard window. So you have that. So you see that when you do the derivative, it looks like there's going to be a vertical asymptote there. Plus the fact that, let me turn off the derivative graph first. There's a vertical tangent at x equals 1. So to say the slope is 100 just seems really awkward, whereas the other one seemed a little more reasonable, like -2 or 1, or sorry, 2 or -1, seemed a little more reasonable. That just seemed weird to me. So that's why it's not going to be defined there. And the end derivative does lead us to a misleading result, because the derivative of that is not going to be, if you were to work that out, it would not be defined. It would not exist at x equals 1. And again, when we do go through the shortcut rules, it'll make more sense. And more of the same stuff. If you want the left hand, so which one's equal to the left hand derivative f? Obviously, that's just 2, just it's a linear function. And the other one's going to be 2x for the right hand derivative, but you plug in 0, and then you'll get 0 at that point. I think that was what was being asked for that one there. So I kind of realized this homework might have been a little bit too advanced, but if you'd like to redo it, or if you haven't, or you got stuck on it, that's totally fine. Because once you watch a 3-3 video, this is gonna make way more sense. So I might have been a little bit ahead of myself with some of these questions I asked. So that's that'll be those problems. Okay, so doing a quick recap of the stuff we've done so far. So 2-4, one of the big things we talked about was this formula right here, the slope of a curve. F of a plus h minus f of a over h, as h approaches 0. What this does, this helps you find the numerical value of the derivative. So you have a function, and you're told, hey, find me the slope of the curve at x equals some value. So you'd use this when you know what the x coordinate is at the point of tangency. If x cubed minus 2x, you got some sort of funky curve that does this at x equals 2. Whatever that slope is that number right there. That's what this tells you. And you see that. That's the big takeaway from 2.4. And we did that just a few other times for different functions, right? For 3.1, the big takeaway, and that's what the quiz is going to be on today. The big takeaway was we extended this by saying, okay, well, now the derivative can be expressed like this, as an expression in terms of x. Still the same kind of methodology. Yeah, we have like a point, we want to get close to it. We're trying to find the slope of a tangent line, but we imagine we have a secant line, but those 2 points get closer and closer together. But this is a more general way of expression derivative. And there was some notational stuff we talked about as well. If you see any of these things here, that just means find me the derivative. So then we had to do the algebra and gave an answer in terms of x. And then we found the slope afterwards. We didn't plug in earlier on. We plugged in at the end after we found this. But this is kind of a more efficient way, because once you have the derivative function, then you can plug in whatever you want for x and get a whole bunch of slopes for a lot of different points on the curve. The equation of tangent line should be pretty straightforward. Use point slope form. You guys should know that. Y minus y1 equals m times x minus x1. This represents the slope at a particular x value, which we plugged 5 in. We got the slope, and we got our equation of the tangent line. If you want the normal line, remember, you take the slope of the tangent and do the negative reciprocal. In this case, it would be -1/75. The x value, of course, was 5 because you're told that. The y value 125, just throw in 5 into the original function to get the y value. So a couple other types of problems. And just, on the quiz, whatever version you get, is just going to look like something like this here. I just did a little variation of it, but it's not that much different. So yeah, so follow your notes. And remember, the derivative of a linear function is just the slope itself. Derivative of x squared is 2x. We do need to spend some time talking about this again. We're going to save that for our discussion on some of the worksheets next week. And we're going to do a little demonstration where there's a really cool website where you can actually draw derivatives from original graphs. And it actually does share with you how accurate you are. And I do this as a little competition. Obviously, I'm the math teacher and I've way more experience with this stuff. But sometimes you guys can beat me. So if you can beat my accuracy, there's a funny video that it's from my honeymoon from 6 years ago. My wife and I went to Spain and Morocco, and we were in I think it was Madrid. I can't remember. Flamenco dancer called me up to dance with her. My wife recorded. She's laughing like crazy. So I'll show you guys that video if you guys want to see it. There's some embarrassing stuff there. So if you can beat my accuracy, you have to. So there's a website that I'll share with you guys, where again you'll have like a original function, and you have to sketch the derivative, and then it shows you how accurate you are. Once you get very good with it, it gets to be a little addictive because you want to see if you can beat your previous accuracy score. So that'll be a great practice for next week. Because again, we have a test list in 2 weeks, and I will ask you, here's the original graph, give me the derivative, or I might give you the derivative graph and give me the original graph. So that was the takeaway from 3.1. And remember, derivative graphs, the y values of the derivative graphs represent the slope of the tangent lines on the original graph, or on the original graph, the slopes of the tangent line are the y values on the derivative graph. That's how you have to look at it. So sometimes you make like a 3-column table. You have like x values, and then of course you have your y values for the original graph, but then you have your slope, your tangent lines as well. That's how you can make that connection. In 3.2, we talked about differentiability, the definition of that. And we also talked about ways of classifying lack of differentiability, like discontinuities, corners, cusps, vertical tangents. We talked about left and right-hand derivatives, how those have to be the same to be differentiable, and they're not the same. You have a lack of differentiability. And then when you dig a little deeper, you see, oh, those are finite values, but different corner. Infinite values, but like one's positive, negative, cusp. Both positive, both negative infinity, vertical tangent. And of course, it's not continuous in the first place. Then you say it's not differentiable as well. And we went over like the contrapositive logical statements. We did a bunch of examples here. In numerical derivatives, how to find this in the calculator, how it could be a little deceiving. So the new stuff from 3.2. What was the new stuff? The new stuff was on the alternative definition. And honestly, don't care what you use. If you want to use, you can use this for your quiz today if you like it, or use what we've been using with H. It doesn't really matter to me. But we do have to, what reason why I care about this is on the AP exam, usually the College Board will kind of like put this expression like in one of the choices. Like they'll say, what is the derivative of this? They'll give you like a table or something. Or give us some like bunch of X and Y values, and they'll reference the derivative of this situation. And you gotta be able to recognize that when you see this notation or expression, that is a derivative. A is over here, and f of x is over here. So it's no different than f of a and f of a plus h. Instead of f of a plus h, say f of x. But in this case, x is approaching a because that's the whole point, right? You want these 2 points to get closer together. So it's all the same end goal, just another way of expressing it. So you just have to be comfortable that, when you see that, that just means a derivative, that's all. And there was an example we worked through here where you found a derivative of root x minus 2. So you had f of x here, you had f of 11. You had to go through the whole conjugate bit, go through the algebra, blah, 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 work it out, you get your answer. And there was an IVT for derivatives, which I don't know if I did the best job explaining it. The bottom line is this, is that if you have an interval from -2 to 5, let's say, and you have the derivative of those endpoints, whatever those derivatives are, any derivative in between those two numbers can be had or should show up in the interval from -2 to 5, assuming that your function is fully differentiable, meaning you don't have any corners, you don't have any cusps, you don't have any vertical tangents, you don't have any discontinuity. If you're differentiable, of course, you're continuous, you're not going to have discontinuities either. The continuity is guaranteed when you're differentiable. So you definitely need to know that. So that's really what is happening there. I think there are some other things that I might have got a little confused about. I'm not going to really touch on it because I just don't want to confuse you guys any more than I may have. But the bottom line is this, is that if you have a function that's differentiable in some interval, the derivatives at your endpoints, wherever those are, any derivatives in between can be had. That's what's happening there. So hopefully that's, we're okay with that. Okay, so we're about to start the quiz in a few minutes. Let me kind of talk about worksheet. Let me talk about worksheet 10 actually. So I think I'm going to change things a little bit because I'm not going to have enough time to really do worksheet 9 in great detail and give enough time for the quiz. So let me just talk about worksheet 10. So at least you have a little bit of understanding what to do there. So let me actually stop this recording, make a new recording, and I'll call it discussion of worksheet 10.